Okay, it's time to start. This morning, we are very delighted to have Professor Hongyu Liu to give us a lecture. The title of the talk is on the geometric principle in wave scattering and application. Let's welcome.
Okay. Good morning, everyone. It's really a great pleasure and honor to be here to give a talk. And actually, this morning I was informed very late, and so that luckily I can catch up my talk. I really didn't expect there are still so many audience here. Anyway, that's given me the motivation to be really careful in my talk. So let me first begin with some background introduction and the motivation of my study. Okay, here is a very simple and a classical scenario about the so-called wave scattering. You see, the left figure is the wave propagate in this homogeneous space, and the right figure captures, depicts this scenario that there is an inhomogeneity called a scatter, and cause the interruption of this wave propagation, produce the so-called scattering. Okay, this is very classical, and in everyday life, like this, our vision is electromagnetic wave. Our sound is, my voice. You can hear my voice because it's a propagation of this sound wave. All those things. Okay. And so here for our study, we are interested in understanding the quantitative correspondence between the geometries of the scatter and the corresponding scattering patterns. Okay, and in particular, we are interested in extracting the geometric feature of this scatter from the corresponding wave pattern, scattering pattern. All right. So now, throughout my talk, and I mainly consider, to make it simple, mathematically. I do not want to make it so complicated. So, I mainly consider the so-called, this scalar wave casing, this hyperbolic PDE, and if you do this temporal Fourier transform, you get this so-called Helmholtz casing. It's negative Laplace u minus omega squared u is 0, and so omega is the frequency. All right. So I just focus on this simple PDE. Definitely, I can make it. After at the end of my talk, and I'm gonna attend to this much more general case like this. Vectorial wave, electromagnetic wave, elastic wave, or this quantum scattering, magnetic Schrödinger equation, and all the other type of waves. But this year, similar feature. Okay. So now, let me give a simple illustration. So this is so-called, extract the geometric feature of this scatter from this corresponding scattering pattern, the so-called inverse scattering. The left figure, this is a true scatter. There's three small scatterers. The right figure gives the reconstruction of these three scatterers from the corresponding scattering pattern. So you can see, we can only find the location of this scatter. We lost track the feature, the fine details of this scatter because it's limited by the physics. There is a so-called diffraction limit. So we can only see the roughly the location because this scatter are too small. Okay. Here is the big scatter. You can see we can reconstruct this as a big scatter. So here, when I talk about these examples, I talk about some very important concept, notion, the smallest, and big, small. But here in this physical world, when you talk about big and small, you have to be calibrated with something. Actually, the size in the wave scattering is to be calibrated with respect to the wavelength. The wavelength is this 2 pi over this omega. And omega is the frequency. This is the calibration. Okay. So actually, based on this calibration, we got 3 cases. Okay, this is the static case. It's omega times this diameter d is 0, and omega times this diameter, the geometric size is this diameter with d. It's known is non-dimensional. Okay, so this is omega times this diameter. This geometric size is much smaller. This is the small size, and it's beyond this quasi-static case. This is the big size. Okay, so we get these two scales: the small and the big. Okay, based on this frequency and our geometric dimension, geometric size of this scatter. Okay. Now, the smallest actually brings a lot of good things, from the, both from mathematics and physics. Actually, let's consider this, from the mathematical point of view. The inverse problem, as I mentioned before, can be, formulated as solving this equation: fx equal to y. You're given this y, we're not find this x. Okay, this f is the model. Now, if this x is small, if the object, target object is small, so we can always do the linearization around this 0. Okay, so actually the inverse problem becomes a linear y. So the smaller, the smaller, the more linear this inverse problem is. So the better, the more robust reconstruction you can have. You can see here, you can have a very, very robust reconstruction. This one is the smallest one. You can see here, this is the brightest one. You can reconstruct much, much better. Okay, so that means it's the smallest. Brings a lot of advantages for solving this type of inverse problem. And also, many, on the other hand, from the physics, many peculiar physical phenomena occur only in the nanoscale, in the small scale, and produce many nanotechnologies. Say, for example, this super resolution imaging and the invisibility cloaking. I only give here, this is two examples. This is a perfect lens. It's based on, it's produced by using this negative refractive index material. If this material's refractive index is negative y, so you can actually produce a perfect imaging using this lens. Okay, and also this is invisibility cloaking. So you see, this is a plane wave propagating in the homogeneous space. But here you coat this, this is the blurry the target object. You coat this with a thin layer of material. You can produce this kind of effect. Control the wave, propagate, slide over this surface of this region, and produce no scattering pattern far away. Okay, but these two phenomena have only been observed and realized in the nano scale, in the small scale, not in the big scale. Okay, but now, so a natural question is, what is the cause for this mathematics and physics? That is, what is the essence of smallness? Okay, so we believe there must be some deeper and fundamental sense other than this, physical or mathematical applications. Okay, now this is our geometric perspective. Let's recall the curvature of this two-dimensional case for this curve. Its curvature at this point is defined to be this 1 over r. R is the radius of this osculating circle. So that means if this object is uniformly small, that means on the boundary, its curvature is high everywhere. So that means, now this is our answer. Is fundamental cause is the high curvature, but not this smallest. But definitely this is our viewpoint. But how to verify this? How to verify this? This is our strategy. Let's say we have a peculiar wave phenomena occurs, especially at the interface. It depends on the geometry. Okay, it's in the small scale. But now I want to verify. We're going to prove that that's the same phenomena gonna occurs in the big size. In the big size, but only locally around these high curvature places. So if we can prove this, okay, if we can prove this, that means it is indeed the high curvature is the main cause. Okay, but actually this is geometric principle we have been proved for several different physical contexts. including this so-called plasmonics and the metamaterials, super resolution imaging, and a spectral geometry of invisibility. Okay. So now this is, due to the time limit, this means the geometric principle, global smallness is local high curvature. As I'm going to talk about our study on the spectral geometry of invisibility and the plasmonics. And the geometric principle have been proved to be valid in several other physical contexts. Okay, but now I'm going to talk about some mathematics. How to verify this. The major technical difficulty comes from how to localize analysis. Localize around these high curvature places. Okay. So now let me first talk about this spectral geometry of invisibility. Okay, what do you mean invisibility? Let's consider the invisibility. That means this scatter becomes transparent under this wave scattering. Okay. Now let's consider a classical time harmonic wave scattering scenario. So we get an instant wave. It's as I said, it's governed by this simple, time harmonic wave tracing. Laplace u plus is k squared ui is 0. K is the wave frequency. Okay. And we got a scatter. It's characterized by its pole to omega. Its refractive index is gamma. Now we, when this instant wave meet this, scatter, it generates this perturbation. So-called this US is the, scatter wave, and we consider this the linear wave. I try to make this mathematics as simple as possible. So we got this Laplace u plus this k squared gamma squared u is 0. We got a zeroth order perturbation because this presence of this scatter. So, okay, so this is the total wave, and with that, for notational sake, I said this gamma squared is 1 plus v. So v is, that means v is 0 outside this omega. You get a zeroth order perturbation. Okay. So now this Helmholtz equation actually becomes this Laplace u plus this k squared times 1 plus v u is 0. Okay. So we got two wave equations. One is this, the other one is that. Okay. One describes this instant wave. The other describes this total wave. Okay. Now, if invisibility occurs, that means what? Namely, this scatter is transparent under this wave probing. That means outside this scatter, there are no scattering pattern. It's just this UI. Outside this omega, it's just this instant wave. So U is UI. That means this US is identical. The perturbed wave is identical to 0 outside this omega. So when that happens, if we, that scattering pattern are trapped inside this scatter. So now, if you want to understand this, this non-scattering phenomenon, you have to study the wave inside this scatter. Let's, restrict this total wave and this instant wave inside this scatter. This U is always satisfies this, perturbed Helmholtz equation, wave equation. This V, the instant wave, satisfies this non-perturbed wave equation. But they are connected on the boundary. This is a transmission condition, the classical transmission condition. You can see. So now, if you want to study this invisibility phenomenon, you have to study this coupled PDE system. Okay. Now this is that means if invisibility or transparency occurs, the scattering are trapped inside the scatter. Those trapped modes are called transmission eigenfunctions. This is the so-called transmission eigenvalue problem. Obviously U and V are identically 0 is a pair of trivial solutions. Definitely, we are interested in finding the non-trivial solution. And it can also be shown that transmission eigenfunctions, you get this transmission eigenfunctions, they can be used as the instant wave to generate this non-scattering, phenomenon. So I want to emphasize that this spectral problem were introduced and studied in 1980s, but in a different context. Okay. But from this invisibility perspective, we studied this type of problem first. Okay. Now the spectral properties of the transmission eigenvalues have been investigated intensively in the literature. In particular, this is a non-symmetric. This is non-self-adjoint problem. So that means there might exist complex eigenvalues. But the real eigenvalues, share the similar properties of this declare normal Laplacian eigenvalues. That means they are discrete. They are there are infinite many. So there is the smallest one is ky. The first eigenvalue is ky smaller than k2. It's going to infinity. But there are some other spectral properties about this eigenvalue problem. It's not the focus of my study. But here I only care about this. There exists the smallest transmission eigenvalue, smallest one. There is a lower bound. That means the lower bound means what? The lower bound means, first, since there is a lower bound of the eigenvalue. According to our earlier study, that means if the scatter is of a size small enough, smaller than what? Smaller than this 2 pi over this ky. Smaller than this size, then no transmission eigenvalue can exist. So that means if this scatter is smaller enough, it can't be visible. If you send a wave, it must produce some scattering pattern. Tells you its existence, but definitely you cannot see the details because you lose this resolution. Okay. So now by applying this geometric, that means if k is small enough, the transmission eigenfunction must be identically 0. Okay. Now let's say if the geometric principle I mentioned before holds, that means the transmission eigenfunctions should be vanishing locally around the high curvature places. Okay, the global smallest is equivalent to this local high curvature. Global smallest, if k is small enough, the scatter is small enough, the eigenfunctions identically vanish. Right? If the big scatter, the locally you get a high curvature point as eigenfunction. If invisibility occurs, then the wave must be vanishing locally at these high curvature places. Okay, actually we verified that. You can see here. It's actually I give some two simple illustration. Actually this this is a corner. The corner singularity is I can think of this extrinsic curvature is infinity. Okay, you can get the kite even at this this concave part or this convex part or even at this concave part. Its curvature is high enough. We get this vanishing property. Okay, but actually, in addition to this numerical illustration, we can verify this rigorously that this is really true. And this, we developed some mathematical techniques. It's based on this macro-local analysis. We can localize our analysis macro-locally around these high curvature places. Due to the time, I can give very quickly discussing about this mathematical techniques. Okay, you consider this. Let's consider a simple case with corner singularity. That means the curvature is infinity. Okay, so we consider this the coupled PDE here locally in this region, but we get a corner point. I'm gonna show this eigenfunction. We get this add this two flat part. We get this transmission condition. But I'm gonna have free part here. This sigma is the free part. Okay. But now we're gonna XC. I'm gonna show that this U and V must be vanishing locally around this XC. And how could we do that? Actually, it's based on this integral identity. You use this integration by parts. You can establish the integral. This the left hand side term is this volume integral in this CH. Involve this eigenfunctions V. But this right-hand side term is this, we can only have this boundary integral along this part, okay, this sigma h, okay? Now, the most important thing is how to construct a test function U0 here. It's there this property. It's the energy localized around this XC, but it decays, decays away from this point. But actually, it's this so-called geometric optics solution, okay? We get a phase parameter. We still can do a symptotic analysis in this phase space, okay? And using that, we can establish that indeed this eigenfunctions U and V gonna vanish locally around this XC, okay? But now if it's become a small, smooth shape with this, the curvature is not infinity, but it's large. So now it's a similar trick applies. You can only track this curvature effect in this integral identity. Okay. So now. And then the second property, okay, according to the geometric principle I mentioned is that it had to be some interfacial pattern Indeed, in addition to this curvature effect, we can also show that this transmission eigenfunctions, indeed, it's an interfacial wave pattern. It localized along this boundary. Okay, so this corroborates the geometric principle that it applies to this interfacial wave pattern. So actually, we actually also very rigorously verified that when invisibility occurs, the wave must propagate along this boundary. Okay. So actually, we can also with the techniques is based on this generalized Where's law and this quantum ergodicity. Okay. And here I give a simple illustration. I do not, as I said, I do not want to make it so complicated. I always consider it a simple wave operator. The Laplace U plus is k squared q squared u. 0 u q is constant. We get this y equation with a capital equation, and this u and they are coupled on this boundary. The idea is that we can reduce this spectral problem to a boundary spectral problem using this layer potential theory. So we got this single layer and a double layer. We can reformulate this, equivalently into this spectral problem on the boundary. Okay. So with that, we can further reduce that into this standard form. Into this, A is the operator. It's defined by those integral operator. Minus this y is phi is 0. It's this classical, form of this spectral problem. And actually, with that, with this formulation, we can using this, we can treat this as the pseudo difference operator and find it, we can consider this Hamiltonian flow generated by the principal symbol of this operator, and study this, quantum ergodicity property. Okay, and then using this Where's law, we can show that the decay energy of these eigenfunctions, actually possess some property that it's decay away from the boundary. Okay, so that gives us this boundary localization property. It's boundary localization, boundary localization property of these eigenfunctions. We are in average the sense. Okay, but definitely we can obtain this kind of result by using this quantum ergodicity property to be this, pointwise. We can derive this pointwise estimate. The same thing. Okay, so at least we can rigorously verify that this is, it's true. Okay. So now, it's the last property we, proved. In addition to this boundary localization, we can also show that this boundary localized argument are resonant surface wave. So actually, when they are restricted on the boundary, they propagate on the boundary. Okay, they propagate on the boundary, so they actually oscillate at a frequency much higher than the excitation frequency. Okay, so that means this energy of the wave blows up at the rate much faster than this k squared. And also all this gradient u or gradient v, they oscillate much faster than this k. Okay, that means they form a kind of resident mode. So that means what? For example, if you consider that the radar image, you send the radar wave and to detect the aircraft. So if you get no response, invisibility occurs. So that wave, that's the electromagnetic radar wave, must propagate on the surface of the aircraft and also oscillate much faster, okay, than the excitation frequency. So we actually prove this. Okay. All right. So now let's consider some applications of our theoretical finding. Okay. The first one is that we give a new interpretation of invisibility cloaking. Okay, this is known. This is known from this physical literature. This is a cloaking technique. Okay, so this is the blue region is the target object. Say for example the aircraft. So you coat this aircraft with a thin layer of material, metal material, special material, so it can produce this type of effect. The wave propagate to meet this object, and this cloaking material gonna control the propagation of the wave And to the other side, the wave gonna return to its original path. Like this, you get a stone in the river, and the river flow gonna pass, slide over the surface of the stone and turn straight at the other side. So you can notice, you do not know, there is a stone in the river. Okay, something like that. Okay, so this is, you can see, it's the wave had to slide, have to propagate on the boundary of this, on the surface of this target object, and because it cannot enter too deep inside this scatter, otherwise it can generate this scattering, right? So actually you can see, so this type of invisibility is produced by the physicist. It's artificial in the sense that it is achieved by employing artificially engineered material device. It's the metamaterial coating. Okay, but actually this type of phenomena already exists in the nature. We just discovered that even for the natural material, if invisibility occurs, the wave also, propagate on the boundary and oscillate very fast and slide over this boundary and return to its original path at the other side. So this type, that means what? The metamaterial invisibility discovered by the physicists and the engineers, it's artificially controlled the reproduction of the natural invisibility. This type of phenomena already existed. It's just that we do not know before. Okay? So in this sense, philosophically speaking, so we didn't invent it, since it already existed in the nature. Instead, we discover it, we understand it, and learn from it. Okay, this is just my philosophical point of view. Okay, and the second is the application is that its application to invisibility is that curvature always scatter. It's actually it's a direct consequence of our study. We know that the wave tend to localize at the sharp places, like this lightning. It cannot localize at this high curvature places. But now, because it can generate a very strong scattering, okay? But however, if the invisibility occurs, the wave must vanish at those places, okay? But on the other hand, that means if you send a wave, it's not vanish everywhere. So if this, if there is an object like this aircraft, its wings or its head have high curvature places, it must not be invisible. It must generate strong scattering. It's a direct consequence of our theoretical result. Okay, so in this sense, this type of UFO, I think, is more reasonable from this invisibility perspective. Okay, you can make it invisible. Okay. So now a second application of our study is so-called super resolution imaging. And you can see here, this is this is the wave. For example, we human beings, how to detect this world like this. We always do this. In a lot of technologies. For example, in the medical imaging, in the geophysical exploration, we always send a wave, and generate this scattering. We collect the wave outside this object and use that to observe the data. We're gonna do the imaging. We're gonna find its shape and its geometry, right? This is standard way of doing this. But actually, the waves are much smarter than our human being. The waves detect this. Waves see this object both from outside and inside. Because why? Because I just show there are always some waves. They are always trapped inside this scatter. And also they carries the geometric information of this object. Right? So actually it looks like on the boundary. And moreover, they see if the wave they see inside this scatter, they see much clearly than their observation from outside. Because why? Because the oscillate much faster. It's a resonant mode. So this is the excitation frequency. So this oscillation frequency is much higher than this excitation frequency. So that means the waves is much more smarter. It's smarter than our human beings. They can see from outside. They can also see inside. Actually, C must refine the details of this schedule. So now, the traditional technology of doing this medical imaging, for example, they always miss this part, this information. And now our idea is we propose a new type of imaging process. Is that in addition to this, we do this, detection, sending the wave, collected wave, response wave, to see this object from outside. We also try to find this trapped mode, this so-called transmission eigenfunctions, and use that to do the imaging. Okay, you can see here. Now let's consider a simple example. This is again this the wave equation that I described earlier, and we want to find the shape of this V using this scattering amplitude. For example, this is classical Y. All right, and I skip this numerical, algorithm. I only showed, this is the, reconstruction result. This is the true object is the square, because I used, this is the object is too small. If you do this traditional, imaging, you only find a red spot. Because why? Because you lose the resolution limit. You lose the resolution. You cannot. Our eyes cannot see so small. Okay. So you can only reconstruct this red spot. But now, if you see inside, you can see if you use this trapped mode, you can actually see much clearer. You can actually find this very clearly. It's a square. But now, as I said, you can do this. Combine this. You can combine this video effect from outside and from inside. This is from inside. This is this is the kite. This is the object is a kite. But now if you detect this object from outside, you see this, and if you detect from inside, you see this. Okay. But now you combine these two. Okay. Combine these two. This is the wave. That's the wave do this imaging. You see this. Okay. We combine this vision from inside and from outside. You can find a much better reconstruction. Okay. So that means what? This is our viewpoint. Invisibility enables super visibility. Okay. All right. So this is the Y. This is Y. In this Y scenario, that is the spectral geometry of the invisibility. We verified that this geometrical principle holds. That this global smallness is actually this local high curvature. Okay. Now I'm going to talk about this. Second part of my talk is on this geometry of this plasmonics. I'm going to also show that this geometric principle gonna hold. That this global smallness is actually equivalent to this local high curvature. Okay. So what is plasmonics? It's actually the so-called surface plasmon resonance. It's a resonant oscillation of conducting electrons at the interface between negative and positive permittivity materials simulated by the incident light. It is a non-radiative electromagnetic surface wave that propagates in a direction parallel to the negative permittivity dielectric material interface. You see here is the numerical illustration. Okay. Actually, this is a wave, this electromagnetic wave. This is the inside this, permittivity is negative Y, and outside is permittivity is Y. So this is electromagnetic wave propagate along this interface. Okay. It depends on the geometry of this interface. All right. So actually, this plasmonic material is, reported as this, top 10 technology breakthrough in this Scientific American in 2018. It's a light-controlled nano materials revolutionizing sensor technology. It's actually stepped out the laboratory and produces a commercial impact. Okay. Now I give a simple, it's along underlying mathematics is not so complicated. Let me give a simple illustration. Simple PD example. It actually contains all the essential points of this plasmonics. Okay. Here let's consider this. Let's consider a plasmonic particle of this form. This it's a direct permittivity inside is negative Y, but outside is Y. It's gonna piecewise piecewise constant parameter. You know, this domain is a ball, is a circle of radius 1. Okay. Now we consider this electrostatics. It's this the resistance gamma greater than u is 0. Is it y? And this u, follow this quadratic row, decays as this at the infinity. Okay. So now we consider this Laplace equation with the metric. But this metric got this negative 1 here inside this this ball. Okay. But now if this gamma is positive, that means it's a Riemann metric, for example. It's ellipticity. So it's elliptic PD, you only get a 0 solution. But if you break this ellipticity, you get this negative 1 here. That allows non-trivial solution. That non-trivial solution is called this plasmonic argument. Okay. Now this argument, actually in this sample case, we can calculate explicitly. We know that this both this function u, both inside and outside are harmonic functions. So a harmonic function only get this two form. It's r to the power n into the n theta. It's r to the minus n into the n theta. This r is this r and the theta is the polar coordinates. Okay. So actually, you can find explicitly that when r inside this this ball is Rn times e to the in theta, and outside is r to the minus n e to the in theta. Okay, you can verify that this is actually the solution to this problem. So now, if you consider this this form of the solution, actually it has two salient features. First, its energy is localized on the boundary. Actually, when we consider this argument, the inside of this ball is r to the n. R is smaller than 1 when you go inside. So that means it decays exponentially when you go inside. Outside of this ball is r to the minus n. Okay, r to the minus n, when you get outside, r is bigger than 1. It actually decays exponentially. So that means its energy is going to be localized, concentrated along this boundary r equal to 1. And also, if we treat this the surface wave, that means we take this we take this r to be 1, it becomes this e to the n theta, cosine n theta or sine n theta. So this is resident mode. It's highly oscillate around this boundary. Okay. So actually, these two fundamental properties, the boundary localization and the surface resonance, forms the fundamental physics principle underlying all those plasmonic technologies. Okay. So now it's a natural question. Can we, this plasmonics, as I said, this technology, nanotechnology, so only occurs in the small scale. So now can we extend it to the big scale, and would this also occur in the big scale? Okay. But actually, now let's verify whether these two physical principles also hold in the big scale. Now let's consider. Actually, it's no longer true. That means this type of phenomena, this two fundamental physics principle, no longer holds in the big scale. So now let me give an illustration. Okay. So this is you can see here. This is the small scale. It's just small scale. This is the argument. The energy of this plasmonic argument is going to localize on around this r equal to 1. But now, if we consider this is a big scale, I make this object bigger, and then you can see here. This is this argument, plasmonic argument. They're going to oscillate, not decay, when when you live away from this r equal to 1. Okay. So that means this nanoscale is critical. The smallest is critical. But now I'm gonna show that this our geometric principle also true here is that if even this type of boundary localization and surface resonance is no longer true in the big scale, but in the big scale it's true locally at the locally small places. That means it's a local high curvature places. Okay. Actually, you can see this is the ball. It's a big scale. The big scale is a big ball. It's a material. It's -1 here. Conductivity is -1 here. You send a wave, it produces nothing. You can produce no resonance phenomenon, no boundary resonance phenomenon. But now I take this point, I drag this point to this side and make the curvature higher and higher. Now it's higher and higher. You can see here, when this curvature is high enough, and this boundary resonance phenomenon gonna occur locally around these high curvature places. You can see here. This is I take this part locally. This part out. You can see here. This is a very significant boundary resonance phenomenon. Okay, that means what? That means plasmonic resonance can still occur in the big scale, but only locally around these high curvature places. Okay, so now we're gonna listen to this observation here, numerical observation here, and also we give a rigorous justification. Here I wanna talk about one of my research philosophy. I think this both this numerical and this analysis, and they are just the scientific tools for our research to discover the world. I think not necessary to rigorously define this is analysis, this is numerical. It does not make any sense, I think. Why you have this kind of narrow vision? Okay, so actually I can verify that. Actually, listen to this numerical observation, we get this rigorous justification. I think indeed this is true. Okay, so our mathematical tools we developed is based on this so-called symplectic approach, and this is quantum integral systems. Okay, and actually how to do this theoretical analysis, we have to introduce some you have to connect this spectral theory of this so-called Neumann-Poincare operator. Okay, how to do that? This is, let's recall, this is we want to find a non-trivial solution to this Laplace operator. And, actually we can introduce this linear potential theory again. We represent this solution in this into this single layer. Okay, and then we want to find the non-trivial solution. And we want to find the non-trivial solution. It's actually reduced to study this so-called spectral theory of this spectral problem. This is K star is this so-called double layer potential operator. It's the Neumann-Poincare operator. It's given here, and now this lambda is related to this parameters gamma c and gamma n. It's y must be negative. If it's positive, there's no way. Okay. And that means that the plasma resonant field is induced by this plasmonic eigenfunction in a rather standard way. If we have a clear understanding about this spectral problem, we can study this. We can have a better understanding about this plasmonics resonance. And in order to understand this plasmonic eigenvalue of gamma c, it is sufficient to understand this spectrum of this Neumann-Poincare NP operator. And in order to understand this, the resonant field, so it is sufficient to understand this NP eigenfunctions. Okay, so actually it's reduced. By this kind of reduction is sufficiently to study this, a spectral problem. Okay. Now I'm gonna show that this eigenfunction phi here, have I can characterize this behavior, the quantitative behavior of this phi, with respect to this local geometric characters of this boundary D as a closed manifold, especially its curvature. I'm gonna show this eigenfunction, this phi, gonna localize around its high curvature places on this boundary D. I'm gonna prove this. Okay, so this is the mathematical problem of our study. And how to do that? This critical point is that we treat this integral operator as a pseudo differential operator. Actually, its principal symbol is given here, and you can see this is the principal symbol of this Laplacian. It's related to. It depends critically on this second order differential quantities of this boundary D. This is mean curvature. This is the second fundamental form. So that means the action at this point on this boundary D, when this curvature is high, is also strong. So this is the critical observation. If we get this, actually the rest is just some standard mathematical analysis. Okay. And actually now we do this again. We do this quantization, and this is the eigenpair with this. It's the quantization parameter is related to this 1 over k. It's we do actually we get a technical restriction. We need to assume that this boundary is strictly convex. And now this is the technical restriction. I believe that our numerical show that this is not necessary. Even non-convex case, it's also true. But it's, we cannot overcome this in our mathematical analysis. Okay. And actually, with that, we can actually show that this weighted energy of this eigenfunction locally around 2 points on this boundary. Let's see P and Q on this boundary. We consider this weighted energy of this eigenfunctions around these 2 points. Okay, it's related to this ratio of this weighted volume on this on the two varieties defined by this Hamiltonian, and the principal symbol of this, Hamiltonian flow generated by this principal symbol of this integral operator. And actually with that, it's the reduced, in order to study this curvature effect, it's reduced to analyzing it's the algebraic problem. Okay, we got this is Hamiltonian, it's already calculated as a symbol, right? So this is the algebraic problem. So actually, now let's consider some simple case. That means the 2 points. Their second fundamental form are proportional uniformly by constant beta. And in that case, you can see that the two volumes are related to this parameter. That means the bigger this beta is, the bigger the ratio is. The bigger the ratio is, that means the eigenfunction is going to localize at this point P, and this with the bigger curvature, with the bigger curvature uniformly, the principal curvature is uniformly large. Okay. Actually, this is a simple case, but actually we can relate it to this this weighted volume is actually related to this L2 energy of this principal curvatures around this point. So that's actually this verified rigorously that this eigenfunctions plasmonics resonance actually going to localize around these high curvature places. The smallest is not this essential cause. The high curvature is the main cause. Okay. Now now let's consider some applications. Okay. The one application is this invisibility cloaking. So the invisibility cloaking, in order to make the object invisible, there are many frontier technologies. The metamaterial coating is just the one approach. And another approach is based on this, so-called anomalous localized resonance using these plasmonic devices. Okay, this is already reported in many literatures. I only listed a few. But the idea is that we use the plasmonic device like here. This permittivity material is 1 here. In this cell, it's a negative 1. So in that, we use the dipole to excite this to generate a resonant field. It's so strong to attract all the electromagnetic information locally around this device within this region. You do not propagate outside. But unfortunately, again, this type of clocking phenomenon only realized in the laboratory in the nano scale, in the small scale. Again, in the small scale. But how to make this for example, how to make this aircraft, the airplane invisible? No way. It's too big. But now, using our result, I'm not going to make this whole aircraft to be visible. I can only make this aircraft locally. The high curvature places, like this head, like this wing, to be invisible. Because we proved that. Okay. And also you can produce this so-called again super resolution imaging. This is two extreme ends. You can make it invisible. I can also make it much more super visible. Okay. It's again based on this geometric principle. Because why? Because these high curvature places can produce much stronger resonant field. Okay. So this is just some applications. Okay, finally, as I said, I only talk about this very simple setup. It's based on this Helmholtz operator. It's a zeroth order perturbation of this Laplace operator. But actually, all our studies can be extended to the much more general scenario. And first, for example, if you study the spectral geometry of this invisibility, this is you get this coupled PDE system. It's the P1 and P2. It's two second order elliptic operator. It's one spectral system, the other spectral system. They're coupled on the boundary with the normal system of this boundary operator. Okay, but actually we before I only considered the cases the P1 and the P2 are Laplace operators. But actually you can make it much different second order elliptic operators to have different physical origin. For example, this is a Maxwell operator. For the physics, that means we can consider electromagnetic waves. This Lamé operator, that means you can consider this elastic wave. And also you can make this coupled. For example, this is Laplace operator. This is Lamé operator. You can have this coupled physics waves. One is the acoustic wave, the other is the elastic wave. They're coupled. But still, that we can show that when invisibility occurs, they get this type of all those properties. The geometric principle holds. Okay, we can produce different applications again in different physical contexts. Okay, the second is for this plasmonics, so this polaritic resonances. Right before, I only consider this integral operator. The singular integral operator is the doubler potential of this Laplace operator. But actually, we can reduce that. We can extend this to the general case. This operator is actually can be a general vectorial pseudo difference operator of order -1. That means it's compact operator, or even it's order 0. It could be a non-compact operator. Okay, we can also for example, you consider this elastic wave. It's a pseudo difference operator of order 0. Actually, we can all our analysis can actually be extended to this more general setup, but only some make this mathematics more complicated. But the idea, the essential idea is the same. The physical origin already tells us the direction to go. Okay, so that's some other applications. But it's just different physics produce the different applications. Okay, I think I got here's my collaborators. I listed here. I got many collaborators from different places around the world. Luckily, I think most of the work I adapted to all of them. And my research was supported by this GIF grant and the Hong Kong RGC Joint Research Fund. And because Professor Yang knows this, we are required to report this. Okay, and thank you.
Thank you very much for the beautiful talk, which combines the numeric side and the rigorous analysis in a beautiful way. And particularly, the talk also combines the physics and the mathematics in a profound way. So are there any questions from the audience?
Yeah, very good. That's related to the so-called aperture. We got this full aperture cloaking. That means full aperture. That means no matter which direction you send the detecting wave, and which direction you observe this response wave, you always get this invisibility effect. This is the full aperture. There are also some technology to achieve this so-called limited aperture cloaking. That means only in a certain aperture. For example, I talk here, and you listen here, you hear here, and you cannot hear me. That is limited aperture cloaking. We have different technologies to achieve this full aperture cloaking or limited aperture cloaking. Yeah, you're now here. Actually, I want to say this. Theoretically, if you use this so-called metamaterial cloaking, in the laboratory, the actually in this if it's uniformly small, not necessarily round, had to be uniformly small, you can have this full aperture cloaking. But here I want to show that if in the big scale, I first show that if it's not round, if there have sharp places, it must not be invisible. It must produce the scattering, and let you know its existence. It's the first. And this is second. I also show that if you coat these sharp places with some specially designed material, and you can make it invisible. So that means the round places are perfect. That means what? Either it's not easy to detect. Second, for the other non-round places, I can make it invisible easily. Okay. Thank you.
Other question?
Can you say a few more words about how quantum ergodicity is used here?
Well, okay.
It just sounds like you are using the concentration of eigenfunction. So are you using that it's less ergodic, so you have more concentration?
Yes, yes, you're right. You're right.
So that's the other direction of quantum ergodicity.
Yes.
Okay,
well,
I see.
yes,
so
yes, you're right. You're right.
Your system is more integrable than ergodic.
Yes, yes, okay. Yeah. You're right. You're totally right. You know this much. Yeah. You're right. You're right. It's concentration. I first saw that the concentration of the eigenfunction. Then I use that concentration result to prove this. The resonant field gonna. There's some relation. There's some relation. But the analysis is boiled down to this. Analysis of this concentration of this eigenfunction of that integral operator. You're right. Thank you.
More questions?
Analysis. Like that?
No. Really? No. It's as long as for example, it's a triangle. For example, there is a triangle. You got a corner, right? You got a corner. I proved that it must not. It's the corner. No matter which direction you send this wave, no matter which direction you send the wave, the triangle, this corner, must produce a stronger scattering than the other part. How to say no? That's not correct. That's not my statement. Definitely, you know physics but much better than me. I will not say this. Okay, I'm saying this. You got for example, you got a triangle, you got a corner, singularity. First, if you send a wave, that wave, if there's no response, there is no response. No matter which direction you send the wave, if there is no response, so then that wave must vanish at this corner places. This is the first thing I proved. Second thing, if I send the wave, it's produce this response, scattering. Let's see, I have to use this, let's see. Yeah, it produces scattering. If there is a response, it produces scattering. If you use this response wave to do it reconstructing, I can prove rigorously that these corners are more easily to be detected than the other places, than the flat places. I'm not saying it generates a strong scattering. I'm only saying that because the inverse problem and this locally around that places becomes linear. I can prove that.
Okay.
Yeah, that's no contradiction with the physics. I know that if this the triangle is like this, right? You send the wave in that direction, you might not see him, right? Yeah, I can show that if you can see him, you can see much easily than the other, in the other, this triangle, right? If you can see him, you say it's much easier than here and here, the flat places. Yeah.
Okay, thank you.
Thank you. Thank you.
More questions? I have a naive question. Is there a localization of the active function in the boundary have some relationship to the phenomena in topological insulator, such as
Right. You're right. That's what I'm thinking about. I'm speculating about that. Actually, I'm trying to do that. Actually, Professor Zhu is the expert on this. Actually, it's related to this topologically protected mode. I think for this topologically protected mode, then you consider this. It's still is the local geometric, feature. It's it's locally around these places. But if this topological, this edge, for example, you consider this the global geometry of this edge. This edge is something like this. You get global geometric quantities, like this curvature, like this the other things. I believe there's some global geometric behavior. I believe, but I haven't done anything yet.
Are there any questions? More questions? Okay, if there's no more questions, let's thank our speaker.
Thank you.